Hi, this is Corey at Amplify. In this video, we're going to be going over a few ways that the students will be accessing complex texts. Two of our main goals will be to deepen your understanding of text complexity, but also to describe how the Amplify Science approach to reading supports students in engaging the science and engineering practices and leveraging the cross-cutting concepts in order to make sense of the disciplinary core ideas that are embedded within all of the Amplify Science lessons. Let's go over the Amplify Science approach. You'll see that far left circle is representing the introduction of a phenomenon, a real-world problem to the students, which does take place within a context of purpose, giving purpose to the development of the students' literacy skills, as well as their use of the science and engineering practices and the cross-cutting concepts to make sense of the disciplinary core ideas. Those circles in the middle with the arrows going around it represents the iterative process the students are always going through as they're collecting information from multiple sources and deepening their understanding with the science content they're grappling with, but also building an increasingly more and more complex explanation of the anchor phenomenon. This is also where you're going to find the use of the multiple modalities for the students. They will be doing, talking, reading, writing, and visualizing. And perhaps more important in this case is that all of those things will be connected together as they go throughout the lesson so that they can see that they are collecting information so that they can substantiate the key concepts or their knowledge claims. And then that last circle represents the students being introduced to a brand new problem or context where they'll be asked to take what they've learned, the skill sets that they've honed, and apply it to a brand new problem, which will help you gauge the understanding that the students have developed. Keep in mind that the do, talk, read, write, and visualize approach does allow the students multiple entry points into the curriculum, but also allows them the opportunity to make their thinking visible in different modes besides just writing and talking. So you'll be able to assess them as they're doing, as they are reading, but also as they're visualizing using the simulations and the modeling tools that are offered to them throughout the Amplify Science program. Literacy is an integral part of science. Scientists read, write, listen, and speak in order to obtain, evaluate, and communicate information about the natural world. They explain their findings, conduct research, connect to work of other scientists, and communicate ideas to a variety of audiences. In the Amplify Science program, students learn to read, write, and speak as scientists do as they acquire facility with the academic language and vocabulary of science. Through the seamless integration of science and literacy instruction, students also learn that reading, writing, and talking are essential practices of science, and that all scientists use these practices to gather information, communicate claims, leverage evidence, draw conclusions from data, and share their ideas through oral and written explanations and arguments. The following are the guiding principles for disciplinary literacy in the Amplify Science program. 1. Students can acquire literacy expertise through the pursuit of science knowledge and by engaging in scientific and engineering practices. 2. Attention to disciplinary literacy instruction should begin as soon as students enter school and should continue throughout the grades. 3. Participation in a community is key to acquiring disciplinary expertise in literacy. And finally, number 4, argumentation and explanation are the central enterprises of science, and thus these practices are the focus of reading, writing, and speaking in science. You will notice that there is an even mix of these throughout all of the Amplify Science units. When we are referring to text complexity, we're borrowing again from the three-part model of text complexity that you find with the Common Core State Standards. You can see their Appendix A for this. We are referring to the qualitative aspects and dimensions of the text, but also the quantitative, and of course those reader and task considerations that must be made as well. When referring directly to the qualitative measures, we are talking about the demands on the knowledge of the reader who is making sense of that text at any given time, and this includes the text structure, including all those visual representations, as well as the things that the reader can either leverage to be able to make sense of what they're reading, or perhaps those things can also stand in the way of the reader. It just depends on the situation. To have a better way of thinking about this from an adult standpoint, think about any type of article you might read from a field of science that you're not familiar with. Like, for instance, here's an article, Application of Nuclear Magnetic Resonance Spectroscopy to the Analysis of Organic Archaeological Materials. We can break down that title from the things that we do know, looking at different words and try to make sense of what's going on. But we also understand, looking at this as an academic article that is set up and formatted in a specific way. It has a very specific structure to which we've become familiar with over time. It may have a summary or an abstract, an introduction, and then all these things are broken down in a logical manner using the different headings that you see there. And you also know the process by which this text has come to be structured this way, going through peer review, for instance, so you have an idea of the reliability of the text as well. If you think about the ideas of how structure help us make sense of the text that we're doing qualitatively anyway, think of a text message, and if you were to look at one and not understand how those were structured, you might have a difficult time making meaning from the text that's coming through in that text. So those qualitative aspects and dimensions of the text are very important, and you will see in the Amplify Science program a lot of attention has been taken to make sure that those are there for the students to help them make connections and to continue to practice the multiple modalities together as well as they're accessing complex text. The qualitative measures within the articles, for instance, if we think of the article compilations, are generally very standard, where we have it look a lot like an article would look in an academic journal, but it also has a lot of text features, including tables and pictures and graphs and things of that nature that will help the student make sense of what's going on in the text. But then also, it will be there as a resource for them that they can borrow from as they go through the entire units. And then when you're looking at the quantitative measures, it's much like what you might imagine as you think of the word quantitative. Of course, we're thinking about that sentence length and vocabulary load. There are two aspects of the quantitative measures, really thinking about the length of those sentences, how difficult they are to break down, but also the frequency in which certain vocabulary words will appear, the amount of academic language that's also in that particular sentence or paragraph. To give you a good example, we can take a moment to look at two excerpts of basically the same article. That top box that you see there, that's an excerpt from an external source, and the one below, that's one from an Amplify Science article that you find in the Earth's Changing Climate unit. I'm just going to give you a few moments. Go ahead and read the top one and the bottom one, compare them, and see what the differences are when you're thinking of the quantitative measures. When I advance, we can see with that top box one, we have basically two sentences there as opposed to the bottom where we have four. There are not just a lot of vocabulary words that are loaded into all of those sentences in the top box, but you also see a few words that might, instead of helping the reader, set them back a bit if they're trying to figure out what resulting and dramatic and subsist means when they're going through there as well. But then when you compare that with the article from the Earth's Changing Climate, you notice that a lot of those words are reduced or put into language that help the student move along in the information to decode the more difficult parts of the passage. You'll also notice that there are only a few vocabulary words in these sentences as opposed to there being quite a few of them. But it gives the students a manageable paragraph that they're making sense of the information, taking that information in, but at the same time they're able to process the vocabulary that's there, being able to discuss this with each other and with the class as a whole as they're making their thinking visible. This just gives you the basic breakdown of that. I'm going to give you a few moments to look this over, just what we were just discussing. We see that there are two sentences at the top, one that's 27 words, another that's 36. There are 11 hard words or phrases in that particular excerpt, and then you'll see that there are four sentences, 17, 7, 34, and 8, and the hard words and phrases only 5 in the Amplify Science article. In the Amplify Science program, a lot of care has been taken with the qualitative measures and the quantitative measures. the reader and task considerations, thinking about the multimodal approach, that do, talk, read, write, visualize approach, and this approach is what helps our students be able to access more complex text, not just the articles, but then also within the simulations, for instance, and card sorts and all the other things that they might be doing in the class, such as the evidence gradient tool, using the reasoning tool. All of these are opportunities for the students to be able to access the text, but they're doing that by leveraging the other modalities from the other projects that they have been doing or the other activities that's been going on in the coherent activity sequences. And this is, of course, helping them make connections between the sources of information that they're utilizing as they are making claims and supporting those claims. But then it also helps them as they're developing their literacy skills to see the same set of vocabulary words across the entire unit, to see the same text features used throughout the unit. And while those may fluctuate, they'll notice that things like the diagrams are lining up with the simulations, are lining up with the articles, and this really helps the student make a connection. All right, let's just take a few moments to consider the roles that text might play in the everyday lives of scientists and engineers that are working together and solving problems. Take a few moments to think about it. Of course, there are multiple purposes for text when we're thinking of scientists and engineers working on an everyday basis. We want to get beyond just thinking of them using text in that formal way, such as writing academic articles or lab reports or research articles, but also how they use text to be able to communicate, to enter into scientific argumentation, but how to be able to solve problems on the fly and also be able to collaborate in real time as well. So how they might use text, not just thinking of it in that book form, but also thinking of it as with the simulations and the modeling tools and the card sorts and the different way that students are going to be making sense of what's going on an everyday basis. Scientists do very similar things as well. Here's a nice table that has been adapted from the article that you can see there at the bottom, or the book chapter, thinking about the different roles and functions that text can play when we're considering an inquiry-based investigation. Just take a moment to look over the table, thinking of it thinking of it thinking of it thinking of it There's first three there: providing context for inquiry-based investigations, delivering content, modeling scientific processes. You may find that the texts that have been generated for the Amplify Science program take on these roles quite often, particularly when illustrating this phenomenon that would otherwise be unobservable to the students. But also the text is there for the students for support reasons as well, when we're thinking about secondhand investigations or them conducting research reports, and then their firsthand investigations or those empirical studies or hands-on projects they'll be doing in the classroom. They can utilize the text as a resource, but also as textual information that can help them support other forms of their investigations. You'll find here as well that these texts will not just fall under the read modality, but of course the do, talk, read, write, and visualize modality, because you find these across the unit in a lot of different formats, not just in the article compilations. Before taking a look at the articles in your unit and determining the roles that they will be playing from lesson to lesson, let's take a look at a help article video that is available to help us better understand how to access articles in the Amplify Science library.
To engage in science, students need to read, write, and talk like scientists. To that end, science texts are one of the prominent features of Amplify Science. In grades 6 through 8, these texts come in the form of science articles, and I'm going to show you how you and your students will access them. Articles are available both digitally and in print. You can print a unit's entire set of articles by going to the Printable Resources area of the unit guide and clicking on Article Compilation. You can also order pre-printed articles in the investigation notebooks from Amplify. They can be printed individually as needed from within each lesson that includes reading activities. For example, in Lesson 1.3. You'll find them in the digital resources. Digital versions of the articles live in the digital library. You could always access the library via the icon in the global navigation menu. More often, however, both teachers and students will access the articles from within the specific lessons where they are read. I'm going to show you the student view of accessing the science articles. Here I am logged into lesson 1.3 of the Matter and Energy and Ecosystems unit as a student. As you can see, I am on the lesson brief page, and the articles are available right here in the digital resources. There is a printable version where the PDF icon is here, and here is the digital version. You can click on this and see a preview of the article. From the preview window, you can select full text, which will launch the library in a new tab opened right to that specific article. Usually, though, students will access an article when they get to the specific activity that it's used in. For example, in this lesson, you can see that students will first do a warm-up, then they move on to active reading. When they open this activity, they see active reading guidelines, and the link to the article is right here at the top of the activity instructions. Going back to the teacher account, you can see that student view by clicking off the instructional guide here or by scrolling down. You'll also see a link to the article in the step-by-step instructions, and you can find another link in the materials and preparation for the lesson here. Let's go ahead and launch this text called Sunlight and Life. Now we are in the library, ready to read Sunlight and Life. There is a read aloud option for this article and all other articles in grades 6 through 8. To use that, just select the speaker icon above the scroll bar on the left-hand side of the article and press play. At the top of the digital article, you'll notice some icons. The first one on the left, a shelf of books, provides shortcuts to articles that you recently opened, as well as the full library homepage. To collapse it, simply click it again. The second one, the menu, is the table of contents. Sunlight and Life is actually an article set, which means it contains more than one article. The table of contents will allow you to jump between the individual articles that comprise the set. You can also see how much of the article you have read. On the right-hand side of the digital article, you'll see more icons. The icon with the page with the corner turned up activates Paged View and allows you to flip between the article's pages rather than scrolling down to see them all on one page. Please note that some features are not available in the Paged View. Next, you will see the search icon, which looks like a magnifying glass. Selecting this one will allow you to search the article for specific terms. The pencil and note icon is for annotations and revealed words. Students can use this to keep track of highlights, notes, and bookmarks they've made and words they've looked up. Students can choose whether they want to see only one type of annotation, such as notes, or any combination of the three. Notice that there is also a search bar at the top of the annotations menu. This feature makes it easy for students to search through their annotations, such as to find a specific note that was made. To learn more about how this functionality can be leveraged in the classroom, check out the Annotating in the Digital Library video. Regarding revealed words, here, in the body of the article, you can see words that are blue with dotted underline. This means students can select the word to open an in-context definition given in both Spanish and English. Selecting the word again will collapse the definition. Notice here that when I collapsed it, a small blue check mark showed up above the word. The check mark means the student has looked at it and it has been added to the revealed words. Here it is. The last icon is your library settings icon. When you select settings, you can change the size of the text to your liking and make other customizations, such as whether to show or hide paragraph numbers. And that's it. If you have any lingering questions about the library, please check out the help site or get in touch with our terrific support team. We are always happy to help.
So let's take a few moments for you to go to your specific unit. You're going to find articles in this unit underneath the teacher references on the unit level page. Look down through each one of the articles that are available for your unit. Determine the role that that article plays throughout that entire unit and within a specific coherent activity sequence, so you'll have to navigate to one of those sequences. And then asking the questions, how does the practice of the multiple modalities help students access these texts? And then, of course, how can these texts be utilized in different ways than suggested within the lesson? So you may think of other ways for you to be able to use this texts other than what is prescribed in the step-by-step that you find on the lesson level. So I'm going to give you a few moments to look over your articles in your unit and thinking about these questions and also, of course, the role that that text plays within the unit. And that role may change from lesson to lesson. Students will be using a variety of strategies to make sense of increasingly complex science texts. An approach dubbed active reading, which is a student-centered process of thoughtful, reflective reading where students work to unpack meaning as they read, will be employed by the students. Students will deepen their understanding of a text by leveraging their background knowledge and working to uncover places where they do not understand the text, and to ask and answer their own questions through thoughtful rereading, discussion with peers, and making connections to what they are investigating in the classroom. In this way, active reading situates students at the center of science reading instruction. In order to personalize and focus students' engagement with the text, the active reading approach supports students in making annotations as they read. Student annotations can include questions about the content, ideas, or words that need clarification, comments about the things in the text that are surprising, confusing, interesting, or they need to further investigate. And connections to the outside world and to other disciplines and ideas are also encouraged. Active reading includes guided peer discussions that prompt students to cite evidence from text and discussions and subsequent activities, to reread text for a specific purpose, and to closely analyze the images and data in the text in order to build understanding. Each article becomes a resource to which students can return and refer to as they continue to investigate ideas and to try to solve the unit's central problem. In inviting students to work together to understand the challenging text, active reading takes advantage of the social nature of the middle school learner.
In this video, I'm going to show you how the Amplify Science Library was designed to promote active reading. I'm going to show you the annotations features. Here we are in Lesson 3.1 of the Matter and Energy and Ecosystems unit. In Activity 3, we can see the active reading activity. Here are the step-by-step teacher instructions and the link to the article. Switching over to the student account, we're going to look at this article in the library and explore the annotations features. First, you and your students have the ability to highlight text within the digital articles. Select the text you'd like to highlight and press Highlight. You can change the color of the highlight or change it to an underline by selecting the highlight again. If you want to delete a highlight, simply select Delete. Being able to add an annotation, which is called a note in the library, is an important feature because active reading really encourages students to ask questions and take note of things they'd like to discuss or think more about as they read. To do that, students will select a part of the text, then choose Note in the box that pops up. They'll then enter their thought right inside the note box. And press Save. If they'd like to edit a note, students can just select the note again and edit as needed, making sure to save. The other icon that shows up when you reselect a note is a bookmark. Students can add a bookmark wherever they'd like to remember to return to later. At the top of each digital article page, you and your students will see the annotations icon, which looks like a page with a pencil on it. Selecting that icon will show students all of the notes, highlights, and bookmarks they've made in the article. In the menu that opens, they can choose which type of annotation they want to see. By default, all three are selected, but if, for example, a student only wanted to see their notes and bookmarks, they'd unselect the highlights icon. Notice that there is also a search bar at the top of the annotations menu. This feature makes it easy for students to search through their annotations, such as to find a specific note they made. Searching annotations is helpful in activities where an article is discussed. For example, in Activity 4 of this lesson, students are asked to review their annotations and choose a couple to share with a partner. To do so, students can go back to the article in the library and skim through the annotations that they made. When they find some they'd like to share, they can click the note to edit it and add #share and press save. To find all the ones they identified for sharing at once, students can go back up to the annotations icon and search #share. This will bring up all of the annotations to which they added that share tag. They can then select each one individually to see it in context and discuss it with their partners. After they discuss each note, they will again click into the note and add #discussed and press save. If there are any shared annotations students were unable to resolve in their partner discussion, or any that they felt were interesting and wanted to share with the class, they'd go ahead and add #present and save. When it comes time to talk about the article with the whole class, the student could then use the search bar to find the annotations they had marked with present. The use of these particular hashtags to facilitate discussion and reflection is only a suggestion, however. Please feel free to have students use whichever hashtags you feel would be appropriate. In addition to discussions, sometimes activities will call for students to share their annotations with their teacher by handing them in like they do with so many other activities. In order for the annotations to be submitted to the teacher's classwork, students will review their annotations, answer the question, and press Hand In. Once they do so, the teacher will see the students' annotations and their responses to the questions in classwork. One thing to be aware of is that students cannot hand in annotations from the library. Annotations can only be handed in when the text is embedded in a lesson activity, like this. To review the annotations students handed in, the teacher will open classwork and filter to the specific lesson in which the reading occurred. You can find information about active reading in the program guide, along with insights into the other ways Amplify Science seamlessly integrates literacy and science instruction.
Now that we have a better idea of how to access the articles in the Amplify Science library, as well as how to use the annotation tools, we're going to conclude by checking out one of the lesson videos that are available on the program hub. We'll see how Amplify Science teacher has taken one of the in-class lessons and changed it for remote learning. You'll see that only a few alterations have been made. You're more than welcome to follow along with your Amplify Science teacher's guide, but also just remembering to focus in on how the teacher is leveraging the multiple modalities to help students access complex text.
Hi, welcome to Science. I'm Mr. Darden. Thank you for being here. Phase change unit still, lesson 3.1, where we're talking about liquid oxygen. And we're going to introduce you to the role of molecular attraction in phase change. So to get started with this lesson, we always do a warm-up to get our brains thinking. And what you need to get your brain thinking is your investigation notebook, Amplify's digital platform, or a blank sheet of paper and pen and pencil. If that's the case, then you're going to want to title this lesson 3.1 at the top of your page, Activity 1. Okay, let's get started. Dr. Flores received the below post on the Space Forum and needs your help responding. So first, you're going to read the post, and then we're going to consider our ideas on how we're going to respond. And then there's a sim activity to gather evidence to help back up our ideas and our claims. Okay, So the post goes like this. Student chemist, hey, that's you, from 681I1E0. Subject, question about lake evaporation. So the person says, I read your findings about the lake, but am confused about the argument that the lake evaporated between 2007 and 2009. The evidence shows that Titan first started getting hotter in 2012 when summer began, but the methane lake was still liquid 5 years later in 2007. If the temperature increased starting in 2002, then energy was being transferred into the lake. Why then hadn't it evaporated by 2007? Great question, great post. If you're in an investigation notebook, this is page 64. So how do we respond to that? Well, the digital platform asks us to think about that the user pointed out energy began transferring into the lake as soon as summer started in 2002. Yet the lake still had not evaporated 5 years later when the probe took the first picture. Your mission then would be to investigate how much energy a substance can gain or lose before it changes phase. So you're going to complete these steps in the sim to test the possibility that energy was added without the lake changing phase. So we're going to launch the simulation and then follow these directions here. If you have the digital platform, go ahead and do that. Otherwise, I'm going to do it for people who don't have access to the digital platform. So I'm going to show what would happen for most of them. Okay, transfer out as much energy as you can without causing a phase change. And then afterwards, you're going to answer the questions. Do all energy transfers lead to a phase change? How can you use the information from the sim to respond to the forum users? So that's most people's job. If you don't have access to the sim, I'm going to make another video for you. Everyone, welcome to Science. Thanks for being here. This is activity 2 of lesson 3.1, where we're still in the phase change unit, and we are going to be reading an article during this part. And the article is about the role of molecular attraction in phase change. So let's get started. I wonder if you can explain why the forum user was confused in the last video. Well, Dr. Flores found the forum user who said, basically, summer started. They have evidence that summer started back in 2002, and then there's liquid lake photo in 2007 from the probe. Why didn't it evaporate between them? And so, what were they confused about? Take a second, pause the video, and talk to someone. Talk to someone about this question. What are some things that you could think about that would help them understand the question and what they're confused about? Okay, so we're not really sure, but here's the deal. The forum user brings up a good point. According to the timeline, it had already been summer for 5 years. We know that the lake evaporated by 2009, but if energy from the sun was transferred into the lake, starting in 2002, why did it take so long? Well, let's look at our investigation question, and maybe this will clear things up. Why didn't the liquid methane change phase before 2007? Looking into this question will help us with the bigger ideas from the overall questions and investigations. So I want to discuss, does adding or removing energy in the sim always result in a phase change? We tried it. We tested it during the last warm-up activity. So what happened? Pause the video again. Talk to someone. Remember, look at your notes if you have to, and say, does it or doesn't it? And try to see what you come up with. All right, thank you. So this question here, this question builds on our observations, right? But we'll investigate the question for the next 2 lessons. And this goes back to our investigation question, our bigger investigation question. So this question is definitely different than this question, but the question relates to our bigger investigation question, where we're asking, why does an energy transfer not always result in phase change? So hopefully in your discussion, you noted that transferring energy does not always result in a phase change, right? But we'll be investigating this question for 2 lessons, and Dr. Flores thinks this article will be helpful in answering the investigation question. The article, Liquid Oxygen, discusses how difficult it can be to change some substances into a liquid. It gives us some of the details explaining how that could happen or not. So I'm going to review active reading, and I'll show you how to annotate, show your thinking, some strategies you can use, such as recording questions, annotating diagrams, and our focus strategy for the unit, making deeper connections. So before I read, let's go over the active reading guidelines. Think carefully about what you read. Pay attention to your own understanding. As you read, annotate. Record your thinking is the goal. Highlight those words you don't know. I'm thinking, I don't understand this word. Highlight it. Add notes to record questions. Make connections to your own experience. I experienced this in relation to what I read. Examine all the visual representations carefully. So look at those diagrams and consider how they go together with the text. Pictures, diagrams, what are they saying? And then after you read, it's good to talk about it with people. Discuss what you have read so that you can show what you have learned. So the next video will be me actively reading, so follow along. Hello, welcome to Science. I'm Mr. Darden. This is activity 2, the active reading part of the activity 2, where we're reading Liquid Oxygen, the article. So I'm gonna read it and do active reading, so follow along with me, especially those of you who don't have access to the digital platform. Here we go. Okay, so the reading is called Liquid Oxygen, and I will start with the title. And I'm gonna get rid of me. Okay, so I read the title, Liquid Oxygen. I see the picture, and it's a guy holding a picture of the, whatever that is. Oxygen is commonly found in the gas phase, but scientists can make it change phase into a liquid. So I'm reading at the bottom the caption. So I'm gonna go with the first paragraph. In your daily life, oxygen is everywhere. It's in the air, all around you, and even inside you, traveling from your lungs to every cell in your body. Wow, that's pretty amazing. Traveling from the lungs, everything. So I'm going to make a note of that, and I'm going to say, wow, I really am interested to know how oxygen gets to every cell. That's pretty cool. So I'm just talking about my thinking while I read, okay? And if there's questions, I'll do questions. And if there's other things, I'll do other things. But this is basically where I'm going. You probably think of oxygen as a gas because that's how you encounter it, but it's always a gas. Oxygen can also exist as a liquid with a beautiful blue color. Ooh, maybe that's, I'm going to write that down, beautiful blue color. Is that what is in the picture above? Blue liquid? is oxygen here? Wow, that's cool. That's a good question. However, you'll never see puddles of liquid oxygen on the ground, and you can't buy a bottle of liquid oxygen at the store. Oxygen is very different from water, the most common liquid on Earth. Scientists can produce liquid oxygen, but it's not easy. Why is oxygen gas all around us, while liquid oxygen is so rare? That's a great question. Let's keep reading to find out. So I see a picture with maybe that's that blue, again, blue liquid oxygen. Oh, oxygen is pale blue when it's condensed into liquid. So answering my own question, yeah, it is. Interesting. Okay, continuing on. The role of attraction. Liquid oxygen is much harder to find than liquid water because oxygen molecules aren't strongly attracted to other oxygen molecules. Every substance has a certain level of attraction between its molecules that pulls the molecules toward each other. Ooh, that's interesting. Okay, so it pulls the molecules toward each other. I'm going to make a note of that. So molecules have something in them to pull them toward each other. And this is like pulling a rope or what? Like thinking about that, like what kind of pulling have I ever thought about before? Things that are pulling towards each other. I never pulled a rope before. All right, this molecular attraction is stronger in some substances like water than it is in other substances like oxygen. Okay. Molecules in liquids and solids stay close together because of the attraction between molecules. In the gas phase, molecules are able to move away from each other because they have a lot of kinetic energy. Oh, this is going back to our thinking about kinetic energy. I'm actually gonna, because they have a lot of kinetic energy, this reminds me of the sim where we looked at kinetic energy. It does. But attraction between the molecules still keeps them in the same general area. Different substances have different levels of attraction, but the level of molecular attraction for any one substance is always the same. Well, that seems important. Next paragraph, since attraction never changes for a substance, something else has to change before the substance can change phase. You can think of each substance as always being a game of tug of war at the molecular level. Ooh, there's my rope thing. I'm going to write that down. Game of tug of war. This game has a rope. Just like my thinking of how they pull molecules together. All right, so my connection worked. I thought about that rope pull, and then, oh, they said it's like that. Cool. Attraction is always pulling the molecules together, while kinetic energy allows the molecules to move around. Substances change phase when either molecular attraction or kinetic energy wins the tug of war. And since each substance's molecular attraction is always the same, the change must be in the amount of kinetic energy the molecules have. A large increase in kinetic energy can move molecules so fast that they overcome the pull of attraction and move away from each other. The opposite is also true. A large decrease in kinetic energy allows attraction to overcome kinetic energy and pull the molecules toward each other. Oh, so the pull can be away and towards. So I want to write that somewhere. Yeah. The attraction can be both away from and towards molecules. Cool. Hopefully I remember that. So here's a diagram I'm looking at, substance A and substance B, and the little dots are showing weaker attraction, so that's a substance A, and they seem to be further apart. And substance B has the stronger attraction dots, and they seem to be closer together. And the caption says substance A is a gas and substance B is a liquid. They are at the same temperature. Why is one a gas and one a liquid? Well, they answer the question by saying substance A has weaker attraction, and its molecules have enough energy to overcome the attraction between the molecules and fly apart. Substance B has a stronger attraction, and its molecules don't have enough energy to overcome the attraction between the molecules. Therefore, its molecules stay together. And next paragraph. For oxygen gas to change to a liquid, the attraction that pulls the oxygen molecules forward toward each other must overcome the kinetic energy that pulls them away from each other. Because the attraction between oxygen molecules is weak, a great deal of kinetic energy needs to be removed from the molecules by making the oxygen very cold before their attraction can pull the molecules toward each other. Next section, using attraction to make liquid oxygen. So I'm going to do this next section in another video. Hi everyone, welcome back. Second part of the reading for liquid oxygen. I'm going to finish it up in this active reading of the article. Using attraction to make liquid oxygen. That's where we left off. First paragraph under this heading, scientists use their knowledge of attraction to produce liquid oxygen. They know they need to allow the weak attraction between oxygen molecules to pull them together. They do this by transferring energy out of the oxygen, lowering the temperature of the oxygen molecules until their kinetic energy is so low that they can't overcome the attraction between molecules. The temperature required to turn oxygen gas to liquid is far colder than what's required to turn water vapor to liquid. That's why oxygen needs to be extremely cold to change phase into a liquid, while water doesn't need to be that cold at all. When scientists need liquid oxygen, they can get it by separating oxygen molecules right out of the air. That's pretty amazing. Here's a question I have. They can just pull oxygen out of the air? Oh, wow, that's a good question. Air is a mixture of nitrogen and oxygen combined with small amounts of other gases in water vapor and carbon dioxide. Oh, so they're pulling oxygen from other gases. Since the gases in the air have different levels of molecular attraction, scientists can separate them by sending the air through a machine with different tanks that are at different temperatures. The next paragraph. In the first tank, scientists decrease the temperature enough to condense the water into a liquid. That is, they decrease the kinetic energy of the molecules so the attraction between them can pull the molecules together. So they're kind of using the kinetic energy to pull things together. I'm going to actually make that comment. They are using the kinetic energy to pull the molecules together. That seems important to me. Okay, so the liquid water that forms in the first tank is drained away. Then the remaining gases are put into the second tank and cooled below minus 183 degrees Celsius, minus 297.4 degrees Fahrenheit. That's cold. That's cold enough to make that the molecules in those gases have very little kinetic energy to push molecules apart. Because of this, the attraction between the molecules pulls them together and condenses the gases into a liquid. just like the water in the first tank. This liquid contains the molecules from the remaining gases in the air, including oxygen. The liquid mixture is then moved into a third tank that is heated up just a little so the nitrogen evaporates. The kinetic energy of the nitrogen becomes too strong for the attraction between the molecules, and they escape into a gas. When the nitrogen evaporates, the liquid left behind is mostly oxygen. Now that seemed kind of confusing. Maybe this diagram will help me understand it when I look at the diagram, because I understood some of that, what I read, but man, this diagram really lays it out clear here. So liquid oxygen machine, they were talking about that. So it says here, the gas goes in, that's air containing mostly nitrogen, oxygen, water vapor, and enters the liquid oxygen machine. So nitrogen and oxygen gas are up in here, and then that gas goes to tank 2 after the tank is cooled and water gets drained away. 2, the tank is cooled even more, producing a mixture of liquid nitrogen and oxygen. And then the liquid moves on, and then that liquid has both nitrogen and oxygen in it, but then the liquid oxygen is separated because they warm up this third tank, and the nitrogen gets released and the liquid oxygen is left. Ooh, that's a process. So to produce liquid oxygen from air, scientists use a machine with 3 tanks. Air goes into the first tank and liquid oxygen comes out the last. Whew. Okay, that seems complicated. Oxygen isn't the only substance that's hard to condense because of weak attraction. Hydrogen and methane. Hey, wait, methane. This is what is on Titan. Ooh, remember that. Also have a very weak attraction. So the lake on Titan must have had a weak attraction also. And so are difficult to condense. Like oxygen, these substances we tend to think of as only being gases on Earth. However, also like oxygen, they can become liquid if they are cooled enough. Cooling these substances just a little won't cause them to condense. These gases reach extremely cold temperatures before condensing into liquids. It's all about the attraction. Cool. Hi everyone, welcome to Science. I'm Mr. Darden. This is activity 3 of lesson 3.1 for the phase change unit. Thank you for being here. I appreciate it. We're discussing annotations. We read the article about liquid oxygen. So next we're going to look over the annotations we made while we read and choose some of those to discuss. So we're going to review the different hashtags you'll use to select your annotation. So there's 3 hashtags and 3 steps. First hashtag is hashtag share. Prepare to share. That's step 1. Choose an interesting question or connection to share with a partner. Tag it with hashtag share. Let me show you. All right, so I pull up the reading. I go to my annotations and I look through them and try to find one that I want to share. And I really loved the way that I thought about pulling with a rope, right? And that was one of my favorites. So I'm going to pull this up and I'm going to edit it. When I do, I can add to it with the hashtag share. And when I do, I save that and I'm ready to share that one. I know that's the one I want to share. Next, it says hashtag discussed. So talk to the partner you have or someone about your chosen annotation. So then I will share that with my partner. So let's pull it up again. And so, hey partner, the molecules have something in them to pull them toward each other, like pulling a rope or what? That's my question. And I read this part about pulls the molecules toward each other. It makes me think about a rope and pulling and that sort of thing. So now I've discussed it, so I changed this from hashtag share to hashtag discussed. And I save it. And then my partner would share also, if I had a partner. If you don't have a partner, that's okay. Let's move on to the last hashtag. Hashtag present. And prepare to present. So choose the interesting or unanswered question to present to more people. The class, your teacher, another person, and then you're going to tag it with present. So I'm going to go back to my reading and back to this. And this is the one I want to talk about the most. So I'm going to go hashtag present, and I'm done saving it. And I've done all 3 of those in a short amount of time. Now I'm ready to move on. So go through that. Look for the ones that are most important. Hashtag share them. And then after you pause and talk to somebody, hashtag discussed. And after you feel like you've discussed, pick the one that you want that's going to be hashtag present. Okay. So hopefully you took some time to do that. Hopefully you took some time, pause the video, go back and check through your reading. After you've done that, let's discuss your questions and see if we can answer them as a class. So, what interesting or unanswered questions do you still have about the article? Pause, talk to someone about that. Maybe somebody else you talked to brought up another question for you think is really important. Let's talk. All right. Thank you for doing that. And then what connections did people make between this article and the sim, or did you make between the article and the sim? You're reading the article, you're trying to follow like what the molecules are doing and the kinetic energy and the freedom of movement and adding energy and subtracting, all that stuff with oxygen. What did you connect that to in the sim? Were there things that you did in the sim that helped you remember, oh yeah, I did that in the sim, or oh, I think that's like the sim because. Pause and think for a little bit. Talk to someone around you. Great. Now, what do you think about the investigation question now? Let's go back to that question and think. Why does an energy transfer not always result in phase change? So from the reading, from the sim, from our discussion, from your thinking, why does an energy transfer not always result in phase change? Hopefully you come up with a good answer and you think it through. Review your annotations another time now, the other ones maybe, and then answer the reflection question if you have a second on the digital platform or in the investigation notebook page 65. If you're just writing it, then this is the question. It's the question we do after reading. You're kind of rating yourself. How good of an active reader are you? As I read, I paid attention to my own understanding and recorded my thoughts and questions. Never, almost never, sometimes, frequently, often, all the time. Give yourself a score. Rate yourself on how well you did.
Thank you so much to the Amplify Science teacher for putting that lesson together for your students and for ours. Before moving on to the Amplify Science helplines, just like to remind you that the middle school articles are written to reflect reading expectations for students and to provide appropriately complex science texts that support, link to, and expand their firsthand science learning. The science and literacy instructions surrounding the text scaffold students' access through careful attention to reader and task considerations of complexity. All students read the same core text, and the level of scaffolding for students is adjusted to meet their needs. Suggestions for these modifications can be found in the differentiation brief, which is found on the lesson level, and it accompanies each and every one of the lessons. Remember that when students read while also having other multimodal experiences around a topic, more students are able to access science texts and see their utility in finding information. Not to mention, due to the Amplify Science multimodal approach to vocabulary learning, the difficult science vocabulary found in the articles is generally familiar to the students by the time they're reading about those ideas. Thank you so much for joining us for this webinar. Please keep checking back to the New York City Resources site as we will update that with upcoming professional learning opportunities. And as a reminder for customer care, if you're seeking information specific to enrollment and rosters, technical support, materials and kits, and teaching support weekdays 7 a.m. to 7 p.m., you can reach us at scihelp@amplify.com. You can also call us at 1-800-823-1969. You can also contact us via the Amplify chat icon that you find on the bottom right corner of your teacher's guide. And just as a reminder, these videos are a part of our synchronous office hours question and answer sessions. You are welcome to join us on Wednesday, December 16th from 4 to 5 o'clock, or Thursday, December 17th from 4 to 5 o'clock. We hope to see you there.